8.3 rational functions and their graphs. So this is just basically like 8.2, except a little bit more tricky. When we have something like this, so these are different ways that the graphs could look. We're going to be focusing on these two. Whenever there could be a discontinuity, so if something cancels out like that, that creates a hole in the graph. We'll talk about that. Or whenever we have an x over x like this, we have an x over x, that's going to change our horizontal asymptote. So typically a horizontal asymptote was if we added or subtracted. Our horizontal asymptote, if we have an x over x, will change depending on this. So when we first look at this information, continuous graph means I will not lift up my pencil. Like here, this would be a continuous graph to draw it. Here, I would have to lift up my pencil because of the hole. Discontinuous graphs means that something would cancel out. So in this case, these two things would cancel out. That would make it discontinue. Now, to figure out what number would make this discontinue would be what number makes this 0. So in this place, there would be a hole at x equals -2. Because if I plug -2 into that equation, I would get 0. And you can't divide by 0. We'll get more into that right now. So if I'm looking at this, we first want to factor this part down here. So if I were to factor this, I have x plus 3 multiplied to get 3, add to get -4 would be x minus 3 and x minus 1. The domain will always depend on the bottom of your fraction. So because I have these two right here, I have two domain restrictions. So this will be my discontinuity. Okay, so whatever numbers make this 0 would be discontinuity. So I'm going to have x cannot equal, because this will be my domain, if I set both of these equal to 0, or cannot equal 0, sorry. Okay, x cannot equal a positive 3, x cannot equal a positive 1, so I would add the 3 over, I'd add the 1 over. So when I'm looking at both of these, because neither of these can cancel out, they're both still going to be there. These are going to be non-removable. Non-removable. Now I'm also looking for x and y intercepts. So if I'm going to look for my x and y intercepts, my x-intercept, first if I plug x-intercept means that I'm plugging 0 in for y. If I plug 0 in for y right here, x plus 3, and I'm going to actually leave it like this. So not. So I want to get rid of this division. The first thing I want to do is multiply this whole thing on this side. So to get rid of this division, I'm going to multiply this whole thing on the other side. Now, typically, you don't have to show this step, but I'm going to since this is the first time you're seeing this. So 0 times anything is going to get 0. So I'm actually just focusing on the top of the fraction. So I subtract 3. I'm going to get x is equal to -3. So my x-intercept is at -3. When I find my y-intercept means I'm plugging 0 in for y, because 0 in for x. So again, I'm going to focus on this before I factored, so I can put 0 here. I can put 0 here in both locations, and this will give me my y value. So these two I'll simplify out, which should be 3 over 3, which is 1. So I have two domain restrictions, which would be x can't equal 3 and 1, both non-removable. There you go. I want you to try to do b by yourself right now. So here I factored. So here my points of discontinuity, so that's going to be a domain restriction. X cannot equal -1 because of this. X can't equal +1. Both of them are non-removable because they did not cancel. X-intercept plug 0 in for y. Again, this whole part would cancel, so we just are looking for when the top is equal to 0. We get 5. Plug 0 in for x. You get here, -5 over -1, you get 5 as well. Look at that. So if I look at C, the first thing we're going to do is factor. So it multiplies to get -4 and adds together to get -1. It'll be x minus 4 and x plus 1. So my domain restrictions here are going to be that x cannot equal a positive 4, because what number makes this 0? However, now when I'm looking at this, these two you can only cancel if there's multiplying in between here. These whole things, it all together cancels each other out. So these are removable. Removable. This will create a hole in your graph. We'll get into graphing. So now when I'm looking at this is what my new equation is. My simplified equation is this. But again, I have a whole at 4. 4, x cannot equal 4. So I'm going to find my x-intercept. I'm going to plug 0 in for y. So 0 here, and I would get negative 1 out. I would subtract 1 over my y-intercept. I'm going to plug 0 in for x. So I have y equals 0 plus 1. Add the 1, you get 1. I want you to try to do D right now by yourself. So I factored it. I have 2 non-removable parts. So again, when I get to the graph, I'll show you what that looks like. If I plug 0 in for y, like here, I cannot get anything out because the top has to make 0 in order for y to be 0, so there's no x-intercept. And we'll get into what this means. Here, if I plug 0 in for x, I get negative 16 out. I want you to try to do the next one by yourself, knowing that you cannot factor this right here. You cannot factor it, but there still will be non-removable parts. So I can't factor this, so my domain restriction would be imaginary. So on my graph, I would not be able to see any domain restriction, kind of like that very first graph on the page, how it kind of looked like, that. It could look something like that. I'm not saying it does. That looks like a bird. Caw-caw, caw-caw. So my x-intercept, I actually have 2 different x-intercepts because this top part has to equal 0. So if I set 0 equal to both of these, I have a negative 1 here and a positive 1 here. Plug 0 in for x, and I'll get negative 1/3 out. I'll try to do f by yourself. So if you factor, you have 2 different discontinuity, okay? You have at negative 2, that one's non-removable. I have at negative 1, that's removable. So these 2 cancel each other out, leaving me with 1 over x plus 2. So that's what my graph would look like. Now, if I were to solve this, I set the top equal to 0, because that equal to 0. So if I put the top equal to 0, I would get negative 1. But remember, x cannot equal negative 1, so there's no solution right there. This would be a hole in our graph. There's no solution. If I put 0 in for x, I would get 1/2 out. So now we're going to actually start talking about graphs and what's going to happen with graphs. So we're first going to focus on the vertical asymptotes. Remember, vertical asymptotes is always the bottom of your fraction. I'm not going to get into this. I'm just going to start explaining. The bottom of your fraction, those are going to be discontinuity. So depending on what happens, if it's removable or not, it will depend on if you have a vertical asymptote or if you have a hole. So I'm focusing here, my domain restriction would be x cannot equal 2 or positive 3. Because it would say the 2 make this 0, the 3 make that 0. You can set both of those equations to cannot equal 0 and then solve if you want. Neither of these are removable. Because they're not removable, both of these would be vertical asymptotes. There would be a vertical asymptote at 2, there would be a vertical asymptote at 3. Notice how I labeled it x equals. I want you to try to do b by yourself. Again, the bottom of the fraction will tell you your vertical asymptote. So my domain restriction is at 1 and negative 3. So a vertical asymptote at 1 and negative 3, that's equals my vertical asymptote. What if I have a problem like this? So my domain restrictions, I would find that first. X cannot equal 2 or negative 3. These 2 cancel each other out. That's going to give me the equation 1 over x plus 3. Because this is removable, that's going to create a hole. So now I cross something out. There's going to be a hole where x is 2. How am I going to figure out what this y value is? You take the simplified equation. So if I do 1 over, and I'm going to plug 2 into the equation, 2 plus 3, that would give me 1/5. Again, I'm plugging 2 into my simplified equation. So that would give me 1 over 5. So I have a hole. On my graph, that would create a hole. Anything that does not cancel out becomes a vertical asymptote. So my vertical asymptote would still be left with the x equals negative 3. Once you try to do d by yourself, so I factor on top. I only have one domain restriction, x cannot equal negative 1. That's a removable one, so I can cancel those 2 out. This is my new equation. So I only have a hole. There's no other restrictions here. So this domain restriction creates a hole. So I plug negative 1, because that's where my hole is at. If I plug negative 1 into my equation, negative 1 minus 1 will give me negative 2. So when I talk about vertical asymptotes, horizontal asymptotes. If I kind of go into this, it's saying m, compare the degree to the numerator of m. So if I had something like this, the denominator of n. So it's always looking at these exponents. If if this number is smaller than this number, my horizontal asymptote is always going to be 0. So if it's bigger on bottom, it's always 0. If it's bigger on top, if the number is always going to be bigger on top, there's going to be no horizontal asymptote. No horizontal asymptote. If these are going to be equal to each other, it's going to be the numbers right out in front. So horizontal asymptote. So first I'd look at my leading coefficients. These are my two leading coefficients right here, and they're the exact same. So this is like 1 over 1. When they're the exact same, it's the number out in front. So it's 2 over 1. My horizontal asymptote here would be y is equal to 2 because it's 2 over 1 because my degree here is the exact same. Here, my degree is different. I have more on bottom. I have more x's on bottom. So that means my n here is greater. So if n is greater, then your horizontal asymptote will be 0. The horizontal asymptote would be at y equals 0. Again, because there's more on bottom. So again, if I look at this, there's 1 here. So there's more on top. I have more exponents. I have a higher degree on top. So if I have a higher degree on top, my horizontal asymptote is none. So again, that would be that m is greater and there's no horizontal asymptote when that happens. I want you to do D, E, and F. So my degree here, my leading coefficient is the same. So my horizontal asymptote is negative 2 over 1. Negative 2 over 1 is just negative 2. Here I have a higher degree on bottom. So a higher degree on bottom means your horizontal asymptote is at 0. Here I have a higher degree on top. Higher degree on top, none, nothing. So now we're going to get into actual graphing. So when I'm doing my graphing, there's stuff that I'm going to have to find. I need to find all of this information. We're going to take it step by step. So first thing I'm going to do is factor. So on top, I can factor to be x plus 4, x minus 3. On bottom, I have x plus 2, x minus 2. Okay? When I look at this, this is my domain restrictions. So I'm going to have x cannot equal a negative 2 because that would make that 0. X cannot equal a positive 2 because that would make that 0. Okay? I'm also going to look at my vertical asymptotes. Because neither of these are removable, my vertical asymptotes would be at x equals negative 2 and positive 2. So actually, I'm going to do that right now. Negative 2 vertical asymptote and positive 2. My horizontal asymptote, when I'm looking at this, again, looking at those first two, there's a 1 over 1. Because they're the same, my horizontal asymptote would be y equals 1. Is that 1? So because I have a horizontal asymptote right here, my range would also be y cannot equal 1 because of that horizontal asymptote. I'm going to find my x or y-intercept. Y-intercept is saying that when x is equal to 0. So if x is equal to 0, I'd have 0 squared plus 0 minus 12 over 0 squared minus 4. So negative 12 over negative 4 would give me a positive 3. So at 0, positive 3. 1, 2, 3. I have a point. If I'm looking at my x-intercept. X-intercept is when y is equal to 0. Again, I'm just focusing on this top. I already have this factored, so I can set the equation y equals, 0 equals x plus 4, x minus 3. So this is where x would be equal to two numbers, negative 4 here and positive 3. So negative 4, and I also have a positive 3. So negative 4, 4, and positive 3. 1, 2, 3. 2x equals. I'm actually going to show you what this looks like on the graph so you can kind of see it. Once I have this information, I'm going to actually use this to help me graph it. So it looks like this becomes a U. This is really the only time that you're going to see my hand. And then even though you can't see your asymptote hugs this corner, and your asymptote hugs this corner. Oops, I forgot to write my y-intercept is at 0, 3. My x-intercept is at -4, 0, and 3, 0. I want you to try to find this information right now for this problem. So here I factored. These two cancel out. This creates your whole. So when you do your domain restrictions at -3 and 4, this creates your whole. So this is my new equation that I'm going to be basing it off of. I plug -3 into that equation. So my whole is at -3, -1/7. Before I get into that though, because I have these two domain restrictions, this is a whole. The only vertical asymptote I have here is at 4. So my vertical asymptote is at 4. When I look at my x's, I have more on bottom. So my horizontal asymptote would be at 0. Horizontal asymptote at 0, and that means my range cannot be 0. So that changes my x-intercept. So if you look at my work, I have no solution for my x-intercept because of this range, or this range. So y cannot equal 0. So I have 0, -1/4 for my y-intercept. I have -3, 1, 2, 3, -1/7, something like that. Again, you can put this into your calculator. However, when you do the whole, I should clearly see that there's a hole there, so you can kind of make it big. So because of this asymptote, this is going to hug over here. And here I'm not going to go through that point. I'm going to go through my y-intercept, and it's going to hug over there. There you go. 8.3 tied up in a bow. Have a grand day.